I'm Anuradha Mathur. I've been teaching physics at Modern School Vasant Vihar in New Delhi. We are going to look at some special electrical circuits with resistances. When we have resistances, we can combine them in series, parallel or any other way. That means a combination of series and parallel. Some of the common circuits that we use in the lab are series circuits, in which we have, supposing we have 3 resistances here and this is our circuit. The current flows to R1, then it goes on to R2 and R3. That means the connection for the resistance box R1, R2, R3 should be like this. The key factors in circuit is that the current in all the resistances is the same. In the entire circuit, the resistances of a combined resistance given by R1 plus R2 plus R3. The potential difference across each resistance may be different, which will have to be calculated in terms of the circuit current. So, the potential difference across R1 will be I, the current flowing in the circuit, multiplied by R1. The potential difference across R2 would be I, the current which is flowing in this part of the circuit, multiplied by R2, and likewise we can calculate this. They should all add up to the potential difference across the 3 of them combined. This is for series resistance, and details of this you can see. You can combine resistances in parallel. A parallel connection would look like this: R1, R2 and R3. Notice the resistance R1, R2, R3 as you can see here. One terminal connects all of it on one side, main circuit. Likewise, on the other terminal of each of them is to be connected on the other side. This forms a parallel connection, which means in a circuit like this, the parallel connection may be seen as here, and the current is divided at this point into the 3 resistor branches depending upon the value of resistance. So, if the resistance is more in a particular branch, lesser current would flow in it. If all resistances are equal, the current divides equally into each of those branches. Another key factor is that the potential difference across each resistor is the same. Currents may be different, but the potential difference remains the same. You can have some more details for the resistances in parallel circuit as given here. Resistances can be combined in series and parallel together. One special circuit used in the lab for useful purposes is a Wheatstone bridge. A Wheatstone bridge comprises of 4 resistances. It can be placed in a way that it can give you a branch in which there are 2 resistances in series and another branch in which there are again 2 resistances in series. The 2 branches are connected in parallel. If you notice, the 2 resistances P and Q are in series, R and S are in series, P and Q are connected across A and C, and so are R and S connected across A and C. So, P, Q in series, R and S in series, and across AC they are in parallel. This forms our Wheatstone bridge. You can have a balanced Wheatstone bridge. A balanced Wheatstone bridge is very useful. How? Because you have to have a ratio between P and Q is equal to R upon S, or P upon R is equal to Q upon S, or S upon Q is equal to R upon P, or S upon R is equal to Q upon P. That means, if this ratio is satisfied, you will say that the Wheatstone bridge is balanced. Something like that is achieved by an apparatus used in the lab as meter bridge. In a meter bridge, a wooden board is there on which there is mounted a scale, wooden scale, with a wire of 100 centimeters length. A and C are the two ends of this wire. Broad copper strips make up this portion of the meter bridge. There is a gap between these two terminals, which is marked E here. The metal strip, thick metal strip, continues with a terminal B in the center. This goes along to this terminal. The gap here, which is F, and the terminal at the other end. You can go to the end of the wire moving along this strip, and you are now at point C. This makes up the 4 resistances. How is that? In gap E, you may put a resistance box. In gap F, you may put the resistance box which is marked here. The other 2 resistances are obtained on this wire. A galvanometer is connected between point D with a movable jockey making up the point D whenever it makes a contact on this wire. Supposing this is the contact that we make and there is no deflection in the galvanometer, which means it is the condition for balanced bridge. The ratio of the resistances in the arm E and the resistance offered by AD length of the wire are exactly equal to the resistance F and this particular length of wire resistance, which is 100 minus AD. So, you satisfy the condition for balanced Wheatstone bridge the moment there is 0 deflection in the galvanometer, because you have the ratio of these resistances being the same, and this can be utilized for finding out the value of any resistance for which we do not have the exact value by just using a known resistance. That means finding point D on wire AC where there is 0 deflection, and then 100 minus AD using a suitable formula which uses the ratio of the resistances, you can find the value of unknown resistance. So, you have seen how a special circuit which combines 2 resistances in series and another 2 in series, and the 2 of them are put in parallel, making up a Wheatstone bridge, and a balanced Wheatstone bridge at that, can be used in the lab. So, this is the principle of meter bridge.